This video is going to be kind of a heavy one, so for that I apologize, but I think you're going to thank me for it at the same time. So today we're going to talk about moment of inertia. Okay, now I got to be honest with you, moment of inertia is effectively just like a mathematical construct that was purely created to simplify equations for objects that spin. Now, if you want, the definition itself is kind of questionable because we know inertia is an object's desire to just, maintain its motion. So the definition of moment of inertia is a quantity, thus a number, just a random thing that expresses a body's tendencies to resist angular acceleration. And then that's literally its definition, and it goes on to define itself by the equation because, like I said, it is just kind of defined by its own equation. So let's talk, well, what is the equation for the moment inertia? All right, well, moment inertia, which is an I, is defined as the sum of the mr squareds. So basically what happened was, physicists were doing all sorts of math with objects spinning, and they were like calculating it and all this fun stuff. And like, oh my gosh, this mr squared just keeps popping up. Let's simplify our lives. And so they just said, let's call mr squared the moment inertia. And it's just going to make the math easier because we replaced a whole bunch of symbols with one definition. And it really does work. It makes math a lot easier, but that's why it exists, okay? So if you were to look for a single particle, all right, orbiting something, like literally a satellite orbiting Earth, all right, so rotating around an object, and you did the math for that, then it's just going to be by itself mr squared. Now, if you then say, well, okay, I don't just want to have one particle, I want a physical object that's rotating. Okay, well, that's then made up of a ton of particles. And so then if you had multiple particles, which is, every other object, well, then that's going to be equal to the sum of each individual particle. So it's going to be the sum of the mr squared, and this is what we end up replacing with that letter I because, well, it's just way easier to handle. All right, now, so let's go into what does this mean for us? How do we use it? Things like that. How do we get these moments of inertia? Because every single object that you're going to come across, there's a bunch of standard ones, so I shouldn't say every object, but there's a lot of standard objects, and they all have their own defined moments of inertia. And so I'm going to kind of go through how we got some of those values, and then I'd recommend memorizing the other ones. Kind of important. You're going to want to know them by heart, not going to lie, because it will not be on the equation sheet, but you're going to want to have access to those. So here's how we derive all of them, what they all really mean. So an object with mass will have all of its mass rotating around a single location, but not all that mass is in the exact same location. So when we look at the true definition for moment inertia, it is equal to the integral, which is the sum of all, r squareds dm, because how that mass is, where that mass is going to be changing. All right. So the best way to go through this is just through some examples. All right, so let's talk about if we are changing our mass in a linear fashion. So what we're going to do is here, we're going to have a little dotted line. We're just going to have a bar. All right, and that bar is going to be rotating around this end point right here. All right, so if we look at this bar, it'll be nice, we'll make it like a 3D object there. It's got individual little chunks of mass. Okay, so like if we were to zoom in, that's like a little piece of mass. And so this is how our mass is changing. So that's dm. And that is equal to lambda dx. You're like, Samansky, what's lambda? Okay, so lambda is the linear density of the object. All right, so usually, again, not always, but often it's like, hey, it's all made of the same material, so therefore it's all the same density, so it's just a constant. But you could have it where that density is changing. So total side note, like the doors on my Trans Am, the doors are so massive. I mean, they're huge. because it's a it's a two-door coupe. The doors are like 6 feet long, and so they actually have different thicknesses and different types of metals as you go closer to the hinge versus farther out to the hinge. So that would have a changing density, and you'd have its own equation for lambda. But if it was like, hey, it's just made out of a block of steel, well, then it's just going to have a constant for lambda. All right. So if we are going to look at this spinning bar, it's rotating around an axis here. This would be a radius or distance. You're going to see us use radiuses, distances, and lengths super interchangeably, which is, I'm not going to lie, hyper annoying, but you kind of get used to it. So then this is our final radius, and that would be equal to the length of this spinning bar. Okay? So now if we look at using this equation here, all right, and we want to actually apply it, well, then we said, okay, so the moment of inertia for this bar is equal to the integral of r squared dm. And now we're just going to do substitution on top of substitution on top of substitution. You're going to hate me. I'm sorry, but hopefully this will kind of make things make more sense. And so what we're going to do is we are going to replace this dm. So now it's going to become the integral of r squared, and we'll replace dm with, so let's see, maybe we'll try some colors out today. All right, so we'll replace dm with lambda dx. All right, so that's our replacement. Okay. So then we have to say, okay, so what are we going to do with this? Well, if we then continue on, this is just a constant. So when we look at it again, we can really say, well, I'm going to pull out that constant. And so I've now got lambda times the integral of r squared. Now you'd say it's dx, but in reality, x is our radius. So I'm just going to do a replacement of dr. Like I said, we're going to use radiuses, x's, and like lengths super interchangeably. I am so sorry. It's just kind of how it goes. And so now we've got this. I'm like, hey, I can integrate that. That's cool, no problem. So when I integrate that, I'm going to come back down over here. So when I integrate that, I get lambda times r cubed over 3, simple power rule, and I'm integrating that between L and 0. And so now this gives me lambda times L cubed over 3. You're like, great, Smansky, this still means nothing to me. I know, I get it. I'm just going to put an I equals here. All right, so now here's the thing. Lambda, we should really talk about what that means. All right, let's go a little more depth into lambda. All right, so this is the density. Well, what's density? Well, density, as you know, like if you had a spatial thing, it's mass divided by volume. Cool. But this doesn't have like 3D space to it. It's like super flat. It's just a length. So lambda by itself is equal to mass per unit length because it's linear. All right, so it's mass per unit length. So I can replace this with my cute little color change here. Mass divided by length times length cubed over 3. And now I can simplify this because my 3 is going to become a 2. That L dies. And so what I'm left with is the moment of inertia for a rod spinning around its edge would be 1/3 mL squared. All right, that would be the equation for that. And if you look at, you don't trust me, check it out. Like, just look at my textbook. It's exactly what it's going to say. All right, no big deal. So, boom, done and done. Now that's only if it's around its end. If it's like rotating around its center or something like that, that's a different equation. Okay, so that's how you do it if it's linear. All right, now I'm going to do it in a different way. All right, so let's say we don't have a linear thing. We've got something that has some area to it. All right, so let's talk about an area method. All right, it's got some 3D area to it. So let's just draw a picture. Let's get a spinning disc. Woo! That is what it just. That is the ugliest thing that I have ever seen. That is what just happened. This is supposed to cheat for me and make it into a disk. So let's try that again. Make me into a. What are you doing? Oh my gosh! I swear it worked yesterday. I swear it worked yesterday. Well, you know me. I only do it in one take, so it is what it is. C'est la vie. You know, no one's perfect. All right, so that is now an uglier disk, which hurts my soul, but it is what it is. So let's say it's rotating around here, and it's just kind of going around its axis there. It's spinning. So now if we wanted to look at like a little chunk of area, so this is like a radio. I mean, not a radio. Record. There's your brain. Record. It's the little piece there. All right. So before our DM was this little segment right there. That was our DM up here. It's a little chunk. Here, our DM, how our mass is changing, are these tiny little chunks. Except that is equal to another density. All right. So this is a sigma. All right. That's the symbol they use for that one, if it's just an area-based density. All right. And so it would be that density. And then instead of dx, because it's a linear thing, now it's changing with respect to area. All right. So let's jump ahead here. So I'll try and color coordinate this so it makes a little more sense. So now our sigma is now mass per unit area instead of mass per unit length. And if you remember, the area of a circle is pi r squared. All right. So what that really means is that our sigma is going to be mass divided by pi r squared. You'll see I kind of use lowercase and uppercase r's interchangeably. I probably shouldn't, but bad habit, hard to break. All right. Now, just because I know where this is going, we also want to know the dA, right? All right, what's our rate of change in area? So if A is pi r squared, then dA is equal to 2 pi r dr. Okay? So now now that we've kind of broken down that initial segment, I'm just going to go back to the original equation, original definition for a moment of inertia. So that's I is equal to the integral of r squared dm. So where we start there. Except now, how our mass is changing is equal to something else. So we've got integral r squared. So I'm going to try and do some pretty colors here. So we're going to replace this dm with this guy here. So we've got sigma dA. All right, cool. And then we're going to make another replacement. So then that is equal to, sigma is again a constant, so I'm just going to pull that out. So we have sigma times r squared dA. Well, we know that dA is equal to this. So I'm going to replace dA with 2 pi r dr. And so now you can start to see, hey, now we've got it in R's and DR's. Cool, finally, it took forever. And so I'm going to pull out all my constants. So 2 pi, that's a constant, so I'm going to pull that out. So I've got 2 pi times sigma integral r squared times r, which then becomes r cubed dr. Oh my gosh, I did that d. I like never do those d's. I guess what I do is called a Russian d. That's what my colleague says. He goes, oh, you do those Russian Ds. Well, I don't know. That's how I was taught derivative symbols. All right. So now I've got this. So when I integrate that, so I'm going to come way back down over here. All right. So we're going to go down over here. So I is equal to 2 pi times sigma. I lose the integral because I'm integrating now. So that's gone. Use parentheses now, Samansky. Do better. R to the fourth divided by 4. We're going to integrate that between our radius. So here's my radius. I'm going to just purple. I like purple. Purple's so pretty. All right, so here's my radius of the object. And 0. All right, because if you're at the center, you have 0. And so now this becomes 2 pi, and I'm going to replace now our sigma. All right, so I'm going to replace sigma with what we have over here, m over a, which we know is really this guy here. So this is what I'm going to replace it with up here. So we've got 2 pi times m divided by pi r squared. And then now we've got r to the fourth. We're integrating it from r to 0. So, I mean, the 0 just nukes everything out. So we've got r to the fourth divided by 4. And now we can just start simplifying. So pi's die. R squared makes that a 2. This 2 goes away, makes that a 2. And so what we're left with is I, for this surface, would equal to 1/2 mr squared. So that would be the equation for this guy right here. All right. So I've done linear. I've done, well, what happens if you do it has an area? And so now I'm going to do one more, and this one's going to be based on volume, and I hope I can freak you out a little bit with it. But again, this would work for any shape. So if you can calculate the area, if it was like a spinning disc and you want to do all that fun stuff, you can do whatever shape you want. Just gotta, it's the same format. Okay, so now we're going to, instead of doing area, let's go and let's do volume. All right, so we're going to do some volume. So how do you do it if it's got volume? So I'm going to, why am I a sucker for this? I don't know if it's going to work. We're going to try it. Another slightly, yes! I don't know why it didn't work before, but all right, so doot, fear. Hey, that worked good enough for me. I'm happy about that. Okay, so let's say we've got our thing. It is rotating like so. All right, and now we're gonna have a solid object, but this could be like a donut, you know, whatever. The approach is still the same. So I just want to kind of show you something cool here. And so we're going to now calculate the moment inertia for this object. Okay, so now if we ask, so what's our little piece here? Okay, so our piece here, we've got this from before, so this should look a lot like the area, except now we're going all the way into the object. Okay, so it's also this piece in here. Okay, so it's this whole smash down in here. So we're taking this chunk, and so this is right here how our mass is changing. So that's our dm. Now, we're going to use, of course, a different symbol. All right, so now we're going to use a rho for this volumetric density. And so it's going to be dv. So we had, dx for when it was linear, dA for when it was using area, and now we've got a dv for volumetric. And so when you now do this, you have to say, okay, I have to understand what this means. So let's bust out our fun colors. So our volume is equal to, our density for volume would be mass per unit volume. And then we have to say, well, how do you calculate the volume of this object? Obviously, it's going to be different based on the object. But if you say, well, what's the volume of this object? Well, volume is equal to pi r squared. That's going to give me the area of that top chunk, but then you're going to multiply it by this length here. All right, so that's our length. And again, this would be our radius. All right, so that's our volume. So we're going to need to know dV. So dV is equal to 2 pi r L dr. And so then if you say, well, what then is our density truly equal to? It is now mass divided by V, and we know that V is pi r squared times L. And I use the capital R here because that's our radius of the whole thing, because it's a uniform distribution. All right, so we have all that stuff set up. It's kind of like what you have to do is the very first step, kind of set up, okay, what's volume or area, and then where are the derivatives of that, and how am I going to rewrite this density in terms of those values? And then you get to start subbing it into our fun definition of moment of inertia. So I is equal to the integral of r squared dm. So that's going to be equal to, yay, colors. All right. Whoa, I went too fast. Yeah, I jumped the gun. I was just so excited for the colors. R squared, and we're going to replace dm with our definition for dm, which is rho dv, and we know dv is this, so 2 pi r l dr. Okay, so I'm kind of trying to speed this up because you're like, I see where you're going with this. Hurry up. That's kind of what's screaming in my head. And so now I can basically say, okay, let's pull out all of our constants. So we're going to pull out the 2, the pi. We're going to pull out the density and the length, because the length does not change. It's in the different axis. Integral. So then we've got r cubed dr. Hey, that looks a lot like the area one, doesn't it? All right. Should look very similar. Except now we're just multiplying by length, which should kind of make sense. So I'll just kind of come back here. All right, so we'll go back down over here. So then I is equal to 2 pi rho times length times r to the 4th over 4. And again, we're integrating that from the radius to 0. And so we got the 2, we got the pi, we've got the L. Now, rho we have defined as this thing over here. All right, so I'm going to bring that in. So rho is now replaced with m over pi r squared L. And then we're going to multiply that by r to the 4th from our integral, divided by 4. And now we're going to do some awesome simplification. So pi's die, r to the 4th comes r squared. This dies, L dies, the 4 becomes a 2, and the 2 dies. So this then tells us that for this object, the moment of inertia is equal to 1/2 m r squared, which is, again, interestingly enough, the exact same as it was if it had absolutely no length to it, right? These are the same. And that's because it's not rotating around that length. That length is not affecting its rotation. Like how long it is does not matter. It's only about how far away from that center axis of rotation it is, not how long it is. All right. So if you've ever like worked with something like spinning around, it doesn't really matter how long the object is you're spinning. It matters how far away or how wide the object is you're spinning. So that's why I kind of like this example, because it looks the same. But hopefully that kind of helps you give a good kind of understanding of what's going on here. Now I have one last thing. I know it's a super long video. I'm super sorry for that. But I have one last thing. Okay, so we're going to go back to our rotating thing. And I got to just teach you one last piece of this puzzle. And it's called the parallel axis theorem. All right, parallel axis theorem. Now, I'm going to do the super hyper simple way because honestly, you just got to understand it. And what that means is that the moment of inertia for an object that has like changed where its axis is equal to the moment of inertia around the center of mass for an object. So you're going to say like, hey, here's the object it's spinning. This is its moment of inertia if it spins around its center of mass, kind of like we just did in this example here. This was around the center of mass. So you're going to take that and then you're going to add to that the mass times the distance away from that axis squared, where that distance squared is equal to, this is in like the xy coordinate system, x squared plus y squared. Hey, this looks like the Pythagorean theorem, because it is. All right. So here's our quick example. I'm saying quick because I'm looking at the clock. I'm like, I don't know if it's going to fit on YouTube. It might be too long. I'm freaked out. Hopefully we make it. All right, so here's our rod. All right, now we did a rod, and it was spinning around its edge. And if you remember, when it was spinning around its edge, right, we did it around its edge. And from just the side, when it was around its edge, I was equal to 1/3 mr squared. All right, well, we're going to spin it around its dead center here. All right, so we're just going to kind of spin it around the center. And so let's pretend we're going to start spinning around the center. Now, when you spin around the center, I, for a rod spinning around the center, is equal to 1/12 mr squared. If you don't believe me, Google it. So now what we're going to do is we are going to move this over, and we're now going to pretend we're going to spin it around this axis. Okay, so basically just like what we did before. Now, in theory, if we did this right, hopefully I can, we should get 1/3 mr squared. All right, so let's use our equation to see if I can prove this. So we are going to take our moment of inertia equal to our moment of inertia around the center of mass, which, like I said, is 1/12 mr squared, plus mass, which is an m, times the distance squared. Well, in this case, I'm doing this the easy way. So I'm trying to just simplify this. This is our distance. In reality, we're not going to need to use the x and y coordinate system. So our distance is just going to be this radius. All right, we're going to square it. So it's just going to be times mr squared. All right. Now, if I just basically combine these, just got to do some, basic math here. So I'm going to get these both into 12. So we're just going to do mr squared over 12 plus, all right, we're going to look at this and say, hey, well, this radius, how much did you actually go? Well, that's r, where this whole radius of rotation here is half the whole bar's length. All right, so this r here should actually be an L. Do better in life, Szymanski. My bad. L squared. There we go. So that r is actually equal to L over 2 for that one chunk. So we are going to just do some quick fixing up here. ml squared. I was so used to the r's, my brain just got trapped on that. So then we're going to have m L over 2 quantity squared, which is then ml squared over 12 plus ml squared over 4. And so we want to combine these terms. So ml squared over 12 plus 3 ml squared over 12 is equal to, dun-dun-dun, 4 ml squared over 12, which, as you know, is equal to 1/3 ml squared. Well, hey, that's exactly what we had last time. So this is called the parallel axis theorem. All right, so you can take any shape and you can just move it along this, just add this to it where this is your, your hypotenuse, how far you moved it away from where it was. So obviously a more complicated shape would have some more complicated math, but fundamentally this is what you're doing and it works. All right, I know that was a long one. It was like twice as long as they normally are, but super, I should, I guess, update some software. All right, so I'll see you guys in class. Hope this was fun.